such a pleasure to write on this board. You know, I already forgot that feeling. Blackboard. It's like going back, meeting old friends. And, you know, I would stay here. If you can leave, I would stay here. Okay, so Lagrangian, what is a Lagrangian? Well, let's call it L. By the way, my notation differs from these two, but that's fine. So it's some function that depends on real valid function that depends on both of these sets of variables and two n variables. Well, it's a scalar value, it's a real valid function. In other words, well, what does, well, okay, I'm not going to write abstractly what it is, but it maps this space and including, if you add, well, roughly speaking, it's like R to n to R, but it's not exactly the whole R to n. This space is called the phase space. So, well, this basically is mechanics. This is the foundation of mechanics. You have a mechanical system that is described by n coordinates. You say, well, our space is three-dimensional. What are n coordinates? Well, these are degrees of freedom. These are things that move. They could be, I don't know, some things. You could have hundreds of them to describe a mechanical system. And then, well, it could be angles, it could be lengths, could be certain things, certain variables that could change during the mechanical dynamics. And you just call them all coordinates. These are things that can change. And then you introduce also velocities, so this tells you how fast they're changing. And the collection of both of them, like this. This is a point in a phase space. Just one single point, right? So basically, well, if this is R2n, but basically that's what phase space is. And so you have one point here. It's a Q dot, okay? And mechanical system is, the state of the mechanical system is described at one point. So every point is a state. So you specify, well, the location or the configuration of your system, what all the angles, all the lengths, whatever is needed, the coordinates, and the velocity, so instantaneous rate of change, where they are moving, all of that. So if you specify that, then you get that point. And then the idea is, well, if this is an initial point, well, let's put initial then, what will happen when you turn your time? You move, you start, yeah, this is the initial condition, and then you turn on the movie, and then it starts moving. Okay, and well, and then it moves by itself, based on laws of nature, based on the equations, basically Newton's equations. But all of this is formalization of that. So that's the picture. And for that, well, we introduced this function. What would you say, where does this function come from? Well, this function, this could be any function in general, right? Because we're generalizing that picture. Well, you don't take it too literal. This could be just any function, just take the function. But if you want to be, well, specific, then in mechanics, the Lagrangian is equal to the difference of two terms. One is, well, let me call it E, and the other, well, let's call it B. And so this is what is called kinetic energy, and that is the potential energy. And usually the potential energy doesn't depend on the velocities, but it may. There are situations where it does depend on it. And usually this is not just the arbitrary function, but because it's kinetic energy, so it will be quadratic in velocities. So it may depend on coordinates in some other complicated way, but that's basically the structure. And well, in particular, you could have, well, as an example, you could have, let's say, m over 2 q dot squared. Well, that's kinetic energy of a single particle with mass m. That's velocity squared, and that's m over just single particle. So free. If you just have this, then there are no forces that are, it will just move along straight lines. If you add here the potential, I'll say that, well, conservative, that doesn't depend on the velocities, then basically you get the Newton's equation with the force F, which is minus gradient of that potential. And so what I'm about to say is, well, how do you get these equations? But that's just a very simple example, okay? In general, just think of this as an arbitrary function. Okay, so you have this function, and then you introduce a functional, which is called the action functional. So it turns out that, well, your system can move from one point to another along infinitely many ways, but it does move along a very specific, unique way, which is realized in the nature, that comes from so-called stationary action principle. What is this? It means that among all possible evolutions of dynamics, stationary action principle, only one trajectory is realized, and it is the one that will minimize this functional, which is the action. So while usually it's called S, in this book it's called I, doesn't matter how you call it, it's an integral of a to b of the Lagrangian. That's all it is. So you integrate that. This is a function, this is q and q dot of coordinates and velocities. They depend on time. And so if you integrate, you get a number. Okay, this number is called the action, right? But of course, the value of that number depends on those functions. Well, if you have, well, if this is 1, you compute this, you get one number. If you pick another one, you compute this, you get another number. So, if you want, that's a function on the space of all paths. Because what it does, remember that space that I introduced? So it maps it to reals, right? So you pick a specific q, well, what we call it gamma, which is the curve with fixed endpoints, and it gives you a number, which is s, well, gamma, which is computed that way. So that's what action is. Yeah.
Can it be negative?
Yeah, it can be negative. Why not? Well, if you look at this, usually kinetic energy is positive, but this term is negative. That can be negative. This is bigger than that. That can be negative. What is positive usually is the energy, the Hamiltonian. We'll come to that a little later. So that's the action. And what is the stationary action principle? It basically says that among all possible paths, the ones that are realized, the ones that minimize or make this extreme, either minimize or either they give you the minimum or the maximum of the action. And when I said that the points have to be close to each other, that's so that it indeed minimum and not the maximum. Because if they are not close, then you could get a maximum. Now if you want, if you look at the, say, sphere, and